6, you learned about Newton's third law. Newton's third law in grade 6 said for every action, there's an equal and opposite reaction. And that's absolutely correct. For every action, there is an equal and opposite reaction. But we talked about this yesterday. That way of stating Newton's third law often leads us to a little bit of a misunderstanding as to what's really happening. Here's the way that I prefer to state Newton's third law. Instead of for every action, there's an equal and opposite reaction, we say if object A applies a force on object B two separate objects. When the hand pushes the wall, one force is on the hand, one force is on the wall. When the foot kicks the soccer ball, one force is on the soccer ball, one force is on the foot. When the hand throws the ball, one force is on the ball and one force is on the hand. If we just state it as for every action there's an equal and opposite reaction, we often think that the forces end up balancing. The action force, the reaction force, equal and opposite, end up canceling each other out. They do not, because they're on separate objects, like we talked about yesterday. That make sense? Now, towards the end of hardest, if not the hardest, of Newton's three laws to understand. The example that we left class with yesterday was the window. If I throw a rock at the window and the window doesn't break, the rock applies a force on the window, correct? Does the window apply force on the rock? Absolutely. Is it equal and opposite? Absolutely. Absolutely it is. If the rock hits the window and it breaks the window, does the rock apply a force on the window? Clearly it must have, otherwise the window wouldn't have broke, right? Does the window apply a force on the rock? Yes. Is it equal and opposite? Yes. Okay, a lot of people would say no for that. If the window breaks, oh, it can't be equal and opposite force. Why? It's different. The force that acted on the window broke the window. The equal and opposite force that was on the rock did not break the rock. It slowed down the rock. But the force is still equal and opposite. It just had a different effect. Does that make sense? Now, we can state Newton's third law mathematically when we say when object A applies a force on object B applies an equal and opposite force on object A. We can state that mathematically in the following way. FAB is equal to negative FBA. The force of A acting on B is equal and opposite to the force of object direction, right? If the force acting on object A is to the right, then the force acting on object B is equal to that force in magnitude, but opposite in direction. That equation is not on your data sheet because it's really just a statement of Newton's third law, which you have to know. So if you have to use this, and you might have to use this, then you're just going to take it out of your head and say, well, okay, these two forces are equal and opposite. I'm going to set them equal to each other with a negative sign out in front of one. By the way, if you get mixed up, and instead of putting the negative sign in front of this one, you put it in front of the other one instead, like this, would that work? Yeah, it doesn't make any. Let's take a look at an example that's on your example question sheet that I handed out last week, or a couple weeks ago, I guess it was. 75-kilogram man throws a 5-kilogram medicine ball. You guys know what a medicine ball is? One of those heavy balls, right, that you have in phys ed. The man accelerates backward at a rate of 0.25 meters per second squared. What's the acceleration of the medicine ball? Let's, before we tackle this question mathematically, let's kind of look at big picture. What would you expect to happen here? If you throw a medicine ball and it's heavy, you would expect the medicine ball to go forward, and assuming you're on ice and there's no friction acting here, you would expect you to go backwards, right? Which one? Because the force on the medicine ball is bigger? No, because the mass of the medicine ball is small, right? The forces are equal and opposite. Always. The forces are always going to be equal and opposite. But the effect of the force is different. Just like the effect of the force of the rock on the window was different than the effect of the force of the window on the rock, the effect of the force on the ball, even though it's equal and opposite to the force on the man, the effect of the force will be different. So let's state Newton's third law mathematically again. Let's say FAB is equal and opposite or negative FBA. Besides F being equal to F is also equal to mass times acceleration. So I'm going to say the mass of object B times acceleration of object B, because this is the force of A on B, right? A on B. We're looking for the mass of object B, the acceleration of object B is equal and opposite to the mass of object A times acceleration of object A. Let's make the man the object A, and let's make the medicine ball object B. If that's the case, we're going to say 5.0 kilograms for the mass of object B times the acceleration. That's what we're looking for, the acceleration of the medicine ball, equals negative 75 meters per second squared. .75 times 0.25 is and we're going to say now negative 18.75 divided by 5. That's going to give me what? Almost 4. Gives me negative 3.75 meters per second squared. Let's watch sig figs here, though. How many sig figs should this be? 2. So we're going to say negative 3.8 meters per second squared. We predicted that the acceleration of the ball should be more than the acceleration of the person, was it? Yeah, quite a bit more, right? How come was it quite a bit more? Because the mass of the ball is quite a bit less. The force is the same. The effect of the force is not the same. It was negative. What does that mean? The forces are equal and opposite. That's why I put a negative in front of the F. But why did we end up getting a negative in front of the 3.8? It's going the opposite direction, right? If the man goes forward, the ball goes backward. Now, if we had have defined it the other way and the man's acceleration was negative, then the ball's acceleration would have worked out to be positive, as it should, right? Opposite to the ball. All right, let's have a look right now at worksheet number 15, questions 1, 2, and 3. Do not do question number 4 yet. You will get question number 4 wrong, almost certainly, if you try question number 4 right now. So don't even bother with it. Just go 1, 2, 3 right now, and then we'll do example number, the example that goes with number 4 if we have time after we've done those 3 questions. Let's have a look at number 3, everyone here. It says a 65-kilogram man throws a 200-gram ball. Let's make the man object number 1 and the ball object number 2. The man accelerates backward at a rate of 0.25. The man's hand is in contact with the ball for 0.5 seconds. How fast is the ball going to be moving when it leaves the man's hand? I'm going to say for this one, I named them 1 and 2, I guess, rather than A and B. All right, not a big deal. Instead of saying FAB, I'm going to say F12 is equal to negative F21. Does that make sense? Doesn't matter whether you call them A and B, force of A on B, force of B on A, or the force of 1 on 2, the force of 2 on 1. I didn't mean to do that necessarily, but when I named them objects 1 and 2, I just was consistent with my naming of the forces there. Does that make sense? All right, so let's say M2 times A2 is equal to negative M1 times A1. That's not going to give me velocity, is it? Don't worry about it. I've told you a million times before. You do what you know. Okay, this is a Newton's third law problem. You're throwing a ball. Okay, let's analyze it the same way as we analyze questions 1 and 2, and then we'll deal with how we're going to find the velocity. M2 is the mass of the ball. Here, let's rearrange it, actually. We have the acceleration of the man, so let's find the acceleration of the ball, A2. it's equal to negative m1 a1 over m2. So that's negative m1, negative 65, times a1, which is, let's make that negative 0.25. How come I made that negative? The ball was accelerating backwards, right? Backwards, so I made it negative there. Mass 2 is 0.200 kilograms. When I solve for that, I get an acceleration of positive 81.25 meters per second squared. So the ball accelerates forward. The man accelerates backward. Yeah, the ball accelerates forward. We got an acceleration here that is a lot higher than the acceleration of the ball. Does it seem reasonable? Should it be a lot higher? Yeah, why? The forces are the same, but the effect of the force isn't the same, right? The effect of the force on the ball is a lot more than the effect of the force on the man, because the man is heavier. All right, there's the acceleration. How are we going to find the velocity of the ball now when it leaves the man's hand? How fast is it moving when it was just in the man's hand before he started throwing it? 0, right? We know the acceleration. We know the time. Why don't we just do this? A is equal to delta V over delta T. Rearrange that to solve for delta V. I get A times delta T, 81.25 times a time of 0.50 seconds gives me a change in velocity of 41 meters per second. Now, if the initial velocity was 0, then the change in velocity would be the same as the final, which is 41 meters per second. Does that make sense? Okay, definitely a little bit harder than question 1 and 2, don't you think? But in the end, like, it's not really any different than doing a question like 1 or 2 and then doing a question like we did back in Unit 1, right? It's just 2 questions in 1.